Hello Math 1093, this is Dr. P with Fractions Beyond Fractions. So this is another video in which I'm going to illustrate how to prove a trigonometric identity. And in this video we're going to make a little more use of algebraic strategies for handling fractions, and also continue using a strategy of putting things whenever possible in terms of sine and cosine. That is actually not totally necessary for the identity we're going to prove in this video, which is the one you see in blue there. But it's a pretty robust strategy, so I'm going to try doing it here. You may be able to find a slightly more efficient strategy, but I'll leave that for you to think about after watching the video. Alright, so we're going to try and prove that for all values of theta, 1 plus cotangent of theta squared over cosecant of theta is equal to cosecant of theta plus 2 cosine of theta. Alright, so the way we're going to approach this is, again, we're going to pick one side of this thing to pick on and see if we can make any progress with that. So let's pick this one and just sort of see where this goes. So what I'm going to do is I'm going to rewrite that side of the equation, 1 plus cotangent of theta squared over cosecant of theta. And I'm going to try writing everything in terms of sines and cosines, because I can probably deal with that a little bit easier. That may simplify things. At least I hope that it will. Alright, so I'm going to rewrite cotangent of theta as its equivalent, cosine theta over sine of theta, and that all is squared. And then cosecant of theta as 1 over sine of theta. Alright. Now, it may be tempting at this point to identify things that we have in common, like sine of theta, and cancel them. But we can't do that right now. I mean, 1 over sine of theta is a factor of the denominator, but it's not cleanly a factor of the numerator. It's sitting inside here. There's a 1 being added to it, and everything's being squared. So there's nothing that I can immediately cancel right now. I'm going to have to do a little bit more simplifying first. So the next thing that I'm going to do is I'm going to rewrite the numerator. I'm going to leave the denominator the same, but rewrite the numerator just by expanding that square. So if I expand that square, remember, anytime I have a square, it doesn't matter if the components are complicated or not. If I have a plus b squared, that's always equal to a squared plus 2 times a times b plus b squared. And that's just the result of distributing that whole thing out. If I rewrite this as a plus b times a plus b, and then use the distributive property, this is what I get. Okay, I'm going to use that idea here to expand 1 plus cosine theta over sine theta squared. So that's going to be 1 squared. Let's enlarge that a little bit. 1 squared plus 2 times cosine theta over sine theta plus the square of this thing here, the square of this, cosine theta over sine theta, that's my b squared. So that's going to be cosine squared theta over sine squared theta. Alright, so now I'm going to use a strategy that I did not use in the previous video, but that comes in real handy here. Right now I've got a situation where I've got a fraction. That's the overall structure of this expression. It's a fraction, but within that fraction there are other fractions. I don't like that very much. I would like to avoid having that be the case. So I'm going to get rid of that by multiplying everything in the numerator by sine of theta and multiplying everything in the denominator by sine of theta. In other words, I'm going to take this 1 plus 2 cosine theta over sine theta, just doing a little bit of housekeeping up top here. So I'm going to take the expression I had in the previous step and multiply by sine of theta over sine of theta. So that's what we in the business like to call a fancy form of 1. It's a fancy form of 1 because I'm just talking about sine theta over sine theta, that's equal to 1, and I can multiply by that because multiplying by 1 doesn't change the value of anything. And in fact, in this case, it lets me get rid of some of these nasty fractions inside the fraction here. Alright, so let's do that. Okay, so how do I multiply these two fractions? Well, I multiply the numerators and multiply the denominators. If I multiply the denominators, I just get 1 over sine of theta times sine of theta. That's 1. And that's the entire reason I'm doing this, really, is that this is going to make things a lot simpler. Alright, what about the numerator? Numerator is going to be, well, I need to multiply this entire thing by sine of theta. So I'm going to distribute the sine of theta through and get sine of theta plus 2 cosine theta over sine theta times sine of theta. You might have already simplified that, but I'm going to leave it be for just a minute. Plus cosine squared theta over sine squared theta times sine of theta. Okay, that's kind of a mess, but because I'm dividing by 1 here, there we go, that doesn't really do anything, so I can just get rid of that denominator entirely. I mean, I'm just dividing by 1. That means I have just the numerator here, sine of theta, plus, and then 2 cosine theta over sine theta times sine theta. Those sine thetas will cancel out. I'm just dividing by sine theta here. Let me point to that. I'm dividing by sine theta and then multiplying by sine theta. The net result is that I just have 2 cosine of theta. All right, and then finally I have, what's this going to be? This is cosine squared theta over sine squared theta, but I'm multiplying by a sine theta. That's going to give me just the first power of sine theta in the denominator. Okay. By the way, if you want a little more justification of that, here's what it is. It's cosine squared theta, and then the sine squared theta is just sine theta times sine theta, and then I'm multiplying by sine theta over 1. So that cancels one of these factors, leaving me with cosine squared theta over sine theta. All right, things are looking a little bit better. I don't know yet how this is going to end up being equal to cosecant theta plus 2 cosine theta, but I don't know, I feel pretty hopeful about this. Okay, so what now? Well, one thing that might be kind of nice is get everything to have the same denominator here. I've got one fraction term here that has a sine theta in the denominator. It might be nice to have these as well. Now, I realize I already have a 2 cosine of theta, and that's exactly the same as what I have here. So you might anticipate that we could just leave that alone and get a common denominator on this term and add this one with this one. And actually, if you do that, it works out perfectly. But I just want to illustrate that even if you do things a little bit inefficiently, you're not going to hurt yourself. I mean, as long as the algebra stays correct all the way through, taking extra steps usually is not that much of a harm. Okay, so I'm getting everything to have a denominator of sine of theta. Okay, the way I did that was I just realized I need a denominator of sine theta here, so I need to multiply both top and bottom by sine of theta. That's why I wound up with a sine squared theta there. And here, to get a denominator of sine theta, I need to multiply both top and bottom here by sine of theta. All right, so anyway, what do I have now? I have everything's over sine of theta. Again, I'm just using the principle of fraction addition here. If they all have the same denominator, then I can just add the numerators. Okay, and now you probably notice there's something really nice going on here with this sine squared theta plus cosine squared theta. Let's move that up. Using the Pythagorean identity, I get that that is equal to 1. And I've got 1 plus 2 sine of theta cosine theta over sine of theta. All right, so now for my last little step here, or one of my last steps, I promise, I'm going to split that into 2 separate fractions, because that's 1 over sine theta plus 2 sine theta over 2 sine theta cosine theta. This is kind of a tongue twister here, over sine theta. Okay, let me say a bit more about that step. So I'm just using the principle of fraction addition in reverse here. I knew that if I was going to add these 2 fractions, I could do it by combining the numerators all in one fraction here. This is just using that idea in reverse. If I have this, I can split it into a sum of 2 separate fractions. And, well, what do I have here? I have 1 over sine theta, that's cosecant of theta by the reciprocal identity for cosecant. And here, I have a factor of sine theta up top. I have a factor of sine theta on the bottom. That's being multiplied by 1. So really, this is just 2 cosine of theta. And I know it's not visible anymore, but in fact, that is exactly the thing I wanted to get. So I've now shown through a very, very long chain of algebraic equivalences that this expression here is equivalent to this, equivalent to this, equivalent to this. And I keep following this chain. Everything's equivalent all the way down to this expression here. So that tells me that this expression and this expression, they're equivalent. They always have the same value. So I can put an end of proof symbol on that one. QED. Let's get my pen out there. QED. And we're done. Now, one more thing that you might want to do throughout is put reasons for the steps that are not just algebra. There are some that are just algebra and that you might have been able to follow without much trouble. But steps like this one here, where I ended up with a 1 all of a sudden, that was a Pythagorean identity. And it's a good habit to put reasons like that when they help explain what's going on in the argument. I don't know where else I would put that. I would say here we're multiplying by 1. And multiplying by 1 doesn't change the expression's value. And then you could say here, for example, I'm using a quotient identity. Anyway, you get the idea. I haven't been very fastidious about putting those at every step, and I don't think that you have to be either, as long as your steps follow clearly, as long as they have clear and justifiable algebra in them. All right, anyway, we're going to get more practice on this in class, but I hope that this helped get us started a little bit.